Hello everybody and welcome back to the series. We try to write our kernel from scratch. If you've seen the last video, I've actually worked on quite a few things, but the most important I think was adding the debug information for the kernel in the kernel. So that's bound to make life easier. That's still not finished yet. Still need to figure out how the API for calling the, or rather producing the stack traces should look like. So yeah, today I think I'd like to work or go back to working on our heap allocator. Let's get to that. So head into heap. Here we had some very nice test code, I think. So here's how I imagine this to go. First of all, I want a simple interface. I want an allocator interface, or rather two allocator interfaces. Yeah, so two allocator interfaces. One for a basic heap allocator, and the other for a page allocator. Okay, so let me just put this here. Design goals. I can type. Right, so second goal here is I want this to handle basically memory allocation and virtual mapping. So I don't want to do the mapping after the allocation has been done. And then for both types of allocators. Okay. So third of this, I want the memory basically handled by this allocation mechanism. Let's go for that term, to be growable. So I don't want to give this allocator the full memory that I have at my disposal to use. So I'd still want to keep keep control of how much memory this should be using, and probably call into the API to let it grow its memory and decide by how much. So the ideas, right? So first is the allocator interfaces is simple. So we just need to create a page allocator, Not sure how it's going to go. Probably just page allocator, just a local, well, rather global variable that contains the allocation variable for this. But is it going to be? Yeah, and also hold on. We might want to start thinking about thread safety, because so far we have been running on one single core, so we haven't really been paying much attention to thread safety. So we might want to start thinking about that. We'll go back once we have once we start working on SMP and stuff like that. We might go back and do some more work on this just to avoid surprises. But for now, yeah, let's just start thinking about this. Keep it in mind. So page allocator is simple. So basically, call pmem.allocate pages page. I think call that. We'll check. Then call vmem.map. Then maybe zero out the pages. Right. Okay, but it's not that simple. Yeah, okay. So it's not that simple. 2.1.1 is we actually are going to need a physical page allocator. So we are going to need a page allocator, but also a physical page allocator. Basically returns physical addresses, but it should do the work to quick map them, zero them out if we need to have that happen. Or if we don't have that happen, it should, in debug mode, just write a bunch of characters to them so that we can track errors if we find them. Okay, so physical page allocator. So that means that we need to also have a physical, or rather, we need to have a function allocate physical page. Sure. That takes, for example, a count in number of pages and some arguments like zero out this page or something, or these pages. Physical allocator here, or rather page allocator, is simple because it just calls pmem allocate pages and then calls vmem and map, and then it zeroes out the pages since they are already mapped. If asked. In safety mode, in constants.safety mode, if pages don't need to be zeroed out, probably write a bunch of random? No. What would be the best way to find issues? Best way to find issues would be to write sequences, so something like ABCD, ABCD, or rather ABCD 1, 2, 3. So something like this, ABCD 0, 0, 2, and etc. etc. So that means that if we point to some memory that's bad, we could basically uniquely find it by looking at where we are in this sequence. I'm not sure we are going to go there right this moment, but it should not be random. It should be a known sequence. Sure, and this is an old trick for finding fuzzing the buffer overflows in older applications. Just basically fill a buffer with a known sequence, and when it overflows, you basically get the program counter goes to an address, and from that address, you know where you are in the sequence, and you know where you want to put the next instruction. Right, so page allocator is simple. Then we have the actual allocator. Basically, this one So this one is hard. For the simple reason that we want this to be growable. Page allocator is growable because we just call pmem allocate pages and free pages, and vmem mmap and then unmap, which is basically just mmap with a 0 in the present flag. So this one is hard. The idea for this one is to build a sort of tree structure, not tree structure, no, just sort of heap, subheap list that goes something like this. We have our first heap here, so heap 1, and then this points to heap 2, and every time we grow our memory, we just basically append a heap n to this list. Allocations go something like can while heap dot can allocate, or while not heap that can allocate, we heap is equal to next heap. So once we find a heap that can allocate, that can handle the size and alignment constraints that we want to allocate, then we just allocate there. Otherwise, if we cannot find a heap, we just out of mem. Yes, okay, that's very good. So let's go ahead and do something like const heap is a structure that contains a sure, let's do tracking. Let's do allocation tracking. This needs to be a capital, and here we want to have total available memory. Sure, this would be U64. Starts at, I think we should initialize. Nah, it should be fine. Total allocated memory U64. This would be a 0. Total free, that would be just easy to compute from these two. So should I not just do, yeah, I should probably just do this, right? Total free memory, and just initialize that with everything we have, and then keep these two. Okay, so that's for tracking. We probably to do build a so how do we go about this? We want to build an allocation tracking that basically lets us build a histogram of sizes alignments, so that we can think about optimizing our memory usage patterns. Sure. So here below this, I would probably like to keep an array or a list of every basically size in increments of powers of 2, and for every size we go to for every size we try to allocate, we go to the closer size given its alignment constraints, and we basically track that allocation and that free there. And if we see, we are going to try to build a sort of histogram, and if we see that for some thing we have a sort of peak, then we should probably think about doing something for that size of allocation. Something like some sort of slab allocator or something like that. But for now, let's move. So here I want to have a list, so sub heaps. This one would be a heap subheap list. Sure. And then this one would be just initialized to nothing. So sub heap, probably do that. List. This one would be a so let's get our list linked list into this. This is at import list.zig with doubly linked list, of course. So here is doubly linked list of some type we are going to need. Yeah, so I'm just thinking about how this goes. Let's go for, let's just call it subheap for now. That should be fine. Let's do priv and next. Sure. That would be okay. So const subheap. And this here, so how do we go about this? Let's think. Sure, it's going to be a struct, that's for sure. And here we are going to have an allocator. But now, is this going to be type mem allocator? This is the question. And we probably just go for, yeah, so this is my question here. Do we go for a generic allocator? Or do we go for something more specific? Because I would like to have, a function that can cheaply tell me if I can allocate on this subheap without having to go through the allocation process and fail. So for now, let's just go ahead and do something like, let's just put in a body there. Const allocator, where is this used? Okay, that's fine. So body is at import memory.zig, I think it should be fine. Body, do we not have body on memory.zig? Oh, wait. So what is going on here? Oh, right. Okay, I see. So this one dot body, and then this one goes to body, and yeah, okay. So this one becomes body dot body. Whoopsie. Cool. So this one is a function that takes in a config. Okay, well that's yeah, okay. Okay, that makes it a bit harder to work with, I think. So that means that now this subheap would need to become a function. Subheap that takes in a comp time. Let's call it config. This would be body config. Sure, let's go for this for now. This one returns a type, and this one will return a struct. No problems there. And here in this struct, we are going to get a body with config. And of course, this one here needs to become that. This one here can go. Okay. Very nice. that means that this subheap list will also need to become, okay, well, this is less than ideal, I think. So comp time config body config. Yeah, so I'm just going to mark this as a to do here. To do maybe, just maybe, extract an interface for allocator config. Sure. Just thinking about if we are going to need because ideally I'd like to basically be able to use my body allocator alongside some of the buffer allocators from the standard library. So mainly that's the, or rather the probably fixed buffer is not the perfect example. I'm probably thinking about, so I'm just going to look at this. Yeah, so it basically just, yeah, I guess it's fine. As long as it's just the last allocation that we try to free, it should be fine. But yeah, I want to use my body allocator alongside one of the allocators from the standard library. So we could probably think about something like allocator 2, because allocator 1 was so good, we made allocator 2. So this one would be a struct, and let's try to think about how this interface would look like. Let's, for now, ignore all the things inside this allocator 2. So here, I think we need something like, we basically need alloc. The public functions for this will be alloc, and inside here we are going to need to have a sort of context, which is the classic any opaque thing here, with so I'm just thinking about this. So yeah, actually, we are just going to need to have pretty much the same. Let me just go here. We are going to have pretty much the same vtable as this, except that we are going to add one more thing. So yeah, sure, let's take that there. I'm just going to get rid of all of these because I'm not building a library here. Cool. So let me just add can alloc, and then this would be a const function that takes the any opaque, takes a line usize, takes an alignment of type std alignment, and returns a boolean. Sure. I think that's all we need. So here we need instead mem with alignment, and here, and here, and here. Okay, so this means that now we can actually go ahead and So what is the problem for this one? Right. Okay, so this can go back to being just a const. Let's get rid of that, and that should be okay. So here, now, I think I can go ahead. Can I? Let me just try something. Can I do const body with config alloc, and then this would be a struct that basically, or rather, no, this would be a function that takes in a comp time config, which is a body, come on, body dot body config, and returns a type, and then this type here is a return of struct. No. Yeah, no, actually, yeah, that's fine. So this doesn't return a type. It should probably return an allocator 2, not 3. It's not that good. So here, what we'd like to do is basically create a body allocator, which would be body. Of course, probably just name this inner alloc, which is body with config, right? This doesn't fail or anything, right? No, it doesn't. So I guess we could just call this body, which is the type, and then this would be body, which is a body dot init. No, something like this, and then we do body dot init. I think. Wait, am I missing something here? Local constants. Oh yeah, of course. Inner. And then this is inner dot init. Am I missing something? Does init return self? Oh, okay. So we need to do that. Actually, we need to do body dot init. And then this takes an allocator. Hold on a minute. Yeah, okay. So for this, I think we could pass it permanent allocator. This returns an alloc, yes. Okay, so that's that. This can be tried here. Let's do that. Of course. Body allocator. Sure. So we don't need this anymore. And here we can go ahead and actually hook the pointer to be inner. Yeah, well, this is going to be a problem. This is going to be a problem because now we have this on the stack here and we want this to go here. So this should probably be done inside of body itself. So instead of and then this. Oh yeah, this is actually pretty cool. We could go do this something like this. That runs a stat.mem.allocator, and then this just goes on to return a basically a similar thing that goes. Of course, this needs to be self, which is a pointer to this probably. So self.pointer, and then vtable, which is yeah, I think we need to recreate that. So I think we need to do something like so thinking about this, yeah, we just hook alloc to self dot v table dot. Actually, we could do. Yeah, that's not really interesting. Alloc do resize to self dot v table dot resize choose, and then remap to self dot v table dot remap. Yeah, some of this will need to be changed, of course, but v table dot free. Sure. Okay. Probably do this here for better thing. Cool. So this one here takes vtable, and then this would need to basically map that vtable to, oops. So can alloc would be inner dot yeah, so that's what I was thinking about actually. Can we just go ahead and pull this somewhere in memory here? And go for memory allocator.sig. Sure. And then here we can drop the 2. It's not that good. Const stud is, yeah, we just need stud here. Stud, there we go. Cool. So that means that here, allocator is the allocator. If I go to body, and we can just go ahead and do just this and drop in allocator.sig into that. Can I actually get rid of? Yes, I can do that. There we go. That's much better, I think. So now we just need to hook one more function to this allocator here. That's cool. So body alloc is alloc. Oh wait, no, hold on. Problem. This one still needs to be setmem allocator. So does this one, setmem allocator. So does this one. Yeah, I'm kind of. Maybe that was not such a great idea after all. Right. Okay. So allocator. This is where it all comes to. So now we just need to go ahead and do can alloc. And then this goes to can alloc. So we still don't have this, obviously, but it shouldn't be too hard to write. Famous last words. Context. This is 8.2. Any opaque len use size and alignment, which is the mem alignment. And I think that's all we take, and we return a boolean, and we return true. It wasn't that hard. And so we can do something like equals length, and then we just send this to, and of course, context. I think we can do something with context here. We can just prepare this, and then can do something like so. Right, so how do we know that we can allocate? So we basically need to go to allocate here. So what is the condition that we have? We basically need to find a matching bucket, right? So we probably need that the align size to be less than the total size that we can have. I'm just going to rename this requested length, of course. Of course, we can get rid of those. So if this length here is less than or is more than the full length that we can have, so if length is more than self.memory length, then that's an obvious false. So that's the easy case. Now, what are the other things that we need to look out for? So if we find a bucket, a matching bucket, but all the nodes above that bucket, or just the next node, so the node just before it, is fully allocated, and the bucket itself is empty, then we cannot allocate. Yeah, I think that should be. Let me just actually take this and put that here. Probably this check here could also go somewhere in the actual allocation code, but you know what, problem for another day. So let's go if, let's get rid of this. So if self.buckets of matching bucket dot wait, do we not have do not have helpers for checking that it's empty? I guess not. Dot head is null. So the current bucket that we've matched is null. We basically just need to find the first bucket above that is not null. Wait, hold on. So if we have anything in this head bucket, in this bucket here, how do we need to go about this? Because we are obviously going to need to bucket iterator, right? We are going to obviously need to iterate this bucket. So buckets of matching bucket dot iter. Right. So we need to try to find at least one empty bucket. Yeah. Okay. That's fine. That's fine. So while bucket, let's just call this itercus. So while this, let's call this node, sure. Does this not fail? No, it does not. It's cool. So while iter next, if we have any node, basically, we return true. Because we basically, I could actually do just this. Yeah, because we found one node in that bucket that's free. Otherwise, else, iter is, or rather, let's go var bucket is matching bucket, and then this goes to bucket here, And there, here we go. Bucket is bucket plus 1. We can just do something like this. And here, iter would go to self dot. So while bucket is less than max order. Yeah, I think we could do something like this. Yeah, this is actually very nice. So we could do this. So we just need to basically reach we need to witness the first free bucket at or above this matching bucket here. And if we do that, that means that we can allocate. Otherwise, if we cannot find a bucket, then we are done. We are done so. Right, so let's write a test for this. So test can allocate. Sure, so let me just grab this. And let me grab also, actually no, let me grab this code here. Yeah. Now let me just replace this. Sure. And here we need to create a log because we did not create a log. There we go. So this should do the trick. Now, so here we have this. So this here we called alloc on this, and it triggered a out of mem error. But now what we can do is we can actually call can alloc. So try state.testing dot expect equal so false, and probably alloc dot can yeah, so alloc dot can allocate. Yeah, so we need to add a few things to our interface, which is nice. Let's for now do this and come back to can alloc. Okay, well, this is ridiculous. Cool, let's go for this. Can allocate is it takes what? It takes a size and an alignment. So let's go for No, actually, let me just go ahead and do this. Yeah, so we create a bit of a problem here. We basically need to get all public functions from this, and yeah, you know what? I'm gonna do it. I'm going to do it. So we're gonna take all these public functions here, and we need to add them to our allocator here. Sure, this takes allocator, which should be just ourselves, I guess. const allocator is at this. Just going to import const alignment. Should be just mem.alignment, just to avoid issues, and probably just go here to stud.mem dot goes to nothing. Sure. Does this Yeah, I think that's fine. So so let me just do something like this, and then do just remove all of those. Sure. Now, what is the problem here? What is the error in this original allocator? It's just a type out of mem. Sure. Sure. Let me do this then. Error is, this is not the best, but we are going to live. Is that not public? Whoops, allocator. Should be public, yep. And I guess we should also have, yeah, that's fine, calm down. Probably get rid of this. And const allocator is at import memory.zig, no, memory allocator.zig. Actually, yeah, that was a good idea, actually. Const allocator is, whoops, import memory allocator.zig. Yeah. Dot allocator. Cool. So yeah, you're not happy because of this. That should be fine. That should also be fine. You know what? You'll be fine. So this is our allocator. So const math is stat.math. Sure. And of course, const mem is stat.mem. Wait, what? Allocator is shadowing allocator. Wait, how is that called here then? Oh, it's not defined. Let's go for let's go for set allocator. Yeah, that's fine. And actually, let's do const set allocator is setmem allocator, and just do set allocator here. What's the problem? Oh, okay. Never mind then. I know this is quite duplicated, and I know that we could do something like we can call into allocator and then use that, but yeah, I'm not too bothered actually. I'll be just fine. I'll be just fine. So now that this can actually go to our allocator. No, this still doesn't go to our allocator. So does that mean that we can actually do something like this? Can I have no resize? No. Hold on. What? No, that's not the correct one. Did I not pick these up? Given how much we've copied, let's just go all in, or all out, I guess. Sure. Let's get rid of this now. Okay. Very nice. So now, can we actually go ahead and get rid of all allocators? Right, so this has been done. So let me just add another to do here. Replace all instances of setmem allocator by a wrapped version of our allocator. Sure. So that means that this now has alloc, this has alloc, that's fine. This one should have aligned alloc, that's fine. And this takes in yeah, so just does a call to alloc advanced with return address. Right, and this takes in the size and the alignment. Okay. And then this calls to alloc with size and alignment. And then this calls to row alloc with byte count and alignment, which should be okay. Cool. So now, what was I going to do? Yeah, so I wanted to go to our allocator here and somewhere along the lines of the just here behind free, I guess we could add it up. You know what? Let's find alloc. Yeah, sure. And just before this, we can just go ahead and do can alloc. So self takes in an allocator, a comp time t, which is a type, and a u size, which is the number of the things we want to allocate. So that means that we also need a can create function here. So public function can create. Yeah, okay. So allocator, and this one is comp time t of some type. Then this returns error or otherwise a pointer to a t. Cool. So I think both of these should just get the size and call into let's do this. This one always succeeds, so we are going to return true there. Otherwise, this one here, we basically create a pointer there, but that's not what we want to do. What we want to do is call can allocate with size, can allocate size with alignment. Sure. So this is the alignment, this is the size, and this is the return address. We don't really need that. We're not tracking the checks here. So that goes, and can this actually fail? I'm not sure, so let's just return that. We still don't have that function, so we can go ahead and do, let's think for a second here. So this alloc here basically just sends the alignment as null and lets the other one do the alignment check. So I'm just going to take these two here. That should be okay. So this one here takes a T type, computes the alignment of that type, and then we create an alignment of A, or rather size of A, and then this can go actually. All of this can go. We're just going to do this, and this can allocate size with alignment. Do we use the same thing? No, we need to swap a few things around. So this one here is the alignment. This one here is the number. And what is the third one? Oh, wait, we are missing one more piece of the puzzle. So this one here, we need to alloc with size and alignment. Yep. So this is the one. This takes a size, an alignment, and n, which is just basically 1. Right, and this is here something we need to, so it can alloc with size and alignment. And for our use case, this takes an allocator, a comp time size, sure, that's a usize, and comp time alignment, that's alignment, and then alignment, and then number of items as usize, and nothing else, and returns a boolean. Right. So we should probably just pick this. We need a byte count. That's what we need to send. Can alloc. No. So this .v table. So we're basically going to call into can alloc in the v table. This takes no return address. Just takes. Let me check. We inverted those. So byte count and alignment. No. So this should call some more checks, and then this calls alloc with that, and that. Okay. Sure. So this one goes like so self dot pointer, and then the rest. Yeah, okay. Very nice. So now we just need to adapt everything else we did so far. So can alloc is can alloc with size and alignment. Takes in a allocator. Wait. So I guess that needs to go, right? Am I high? Takes in self allocator, a comp time size, and yeah. So why does it not like that? Can alloc. Oh, I see. So this is the size. Okay, we've messed things up a bit. So size is that, and I guess we need to do this. The alignment is A, and N is the number of items, and here can create. So this can call to can alloc with size and alignment, takes a size of t, right? And N here would just be 1. Okay. Okay. So I'm pretty sure that this here does a few more checks. Let me check here. One of these would basically do this, yes. Whoops. So let me just do this and here. Return true. So we can just skip the obvious cases. Okay. Can create, can alloc. That sounds nice. We'll see. So can alloc. This takes a comtime type, and then takes in a size. But here's one thing I also want to do is bob fn can aligned alloc. This is often useful to allocate, to impose a alignment to a type that doesn't have it naturally. Comtime alignment, which is optional because we just take the type's natural alignment if we don't have it. usize. This also returns a boolean. I think we forgot the return types in a few places, but this goes to self.can alloc with size and alignment. Yep, and this is fairly straightforward. So we get size in size. Is that what we call it? No, we call it n. And then the alignment is alignment right. Oh, wait, actually messed this up. So this is size of t. Yeah, so just actually we could have done something a bit smaller there. Yeah, I think we could have been a bit smarter by just having the most generic function be this one here. Just make it take an optional alignment. And then it should do something like const alignment is comtime. Const a, for example, alignment or else alignment.of t. But here we don't have the t. Right, so let's forget about this. So this cannot be. So can we do can alloc with advanced? Sure. Can alloc advanced, which takes self allocator, comtime t, which is a type, a comtime alignment, which is an option of an alignment, and then n, which is a usize. Then returns a boolean, and then this just let me just block this from here and do return self.can alloc with size and alignment. We have the size, we have the alignment, so we can just go ahead size of t, a, n, and that's all we need. Cool. So now we can just basically use, so can alloc, let's just go for all the cans. Right, so this one here, you can just call can alloc advanced, right? Gives it the t, the alignment, and the number. If we go to the other ones, this can actually go. We can call can alloc advanced with just t, the alignment being null, and sure, that's actually pretty nice. And this one here can also pretty much do the same thing. Hold on, I'm thinking. Yeah, actually, it's fine. This one is easy enough to just leave alone. Cool. Very nice. So this one here, can alloc, takes the type and then the size. No, so now we need to do can aligned alloc, because that's how we are going to fit our alignment into, whoops, so let me just bring this here. This is the, so allocator type and alignment and then n. Okay, so this one here should be false. And if we go just before every other alignment, every other allocation, this one we expect it to succeed, so we can go ahead and do, so from byte units of 64, actually let me just do something like this, and here also do something like that. So let me grab this again and go to just before this allocation and just before this other one. So this one we expect true can create. This is a create. No, this is an alloc. Can alloc self. Rather, this one is a U8. We don't have a type, and we just have number, which is 128 here. This one here, we allocate a U64, rather 3 of those. So something like this. And obviously here, we should probably not do the allocation itself, just in case. So I'm just going to exit this, don't need that anymore. CD into kernel, and here sig build test. Okay, a few issues here. Let me just grab this to the side. Let's go. Mem allocator found, memory allocator. Yes, obviously. So here, somewhere here. Let's think. Let's think about this. Our alloc is body.allocator. Okay. So this will wrap our alloc. Okay. Just thinking about this. Let me just check something here. Allocator, does it have? Yeah. Kinda bad. Kinda bad. Allocator. Okay. Function shadows declaration of allocator. Sure. we are going to go through all of those. And no, hold on 1 second. I try to do this. Okay, so allocator. Oh, right around here. So let's call it self. Oops. Hold on a minute. Okay, cool. Self. Okay. So we need a incompatible types pool and error of whatever. What is going on here? In 747. No, not this one. 747. So what is the signature for this? Can this actually fail? No, it can't. So why? Oh, of course. Of course, so can create. Nice. Just boolean there. Right. So let's see here. Type vtable does not support. Oh, I see. I see. Okay, so allocator. Right around here, I think. So what is your problem? This is a stdmem allocator. So stdmem allocator, right? This vtable here is of type pointer to const vtable, and of course we just forget this. Right, so just go ahead and do that. I cannot read that. So expected type bool, but found error out of memory. Oh, right. Okay. That's fine. 198. So, if the multiplication overflows, then yeah, we don't have enough memory for that. So, return false. It's easy enough. Okay. Member function expected 3 arguments, found 2 in body 750. Wait. Oh, can alloc. Very nice. Okay, so now we have a failure. Integer overflow. How come? In 500. So I think I know where this is. This is right around here. So why is this overflowing? Oh, I see. Because the yeah, let's do the check here. If bucket is less than max order, bucket is of type bucket index, so it cannot reach max order. So we need something else here to break out of this loop. So probably let's do something like this. I'm actually intrigued to know how we went around this before. Oh, I see. Yeah, okay. Because there is a chance that we let's think about this for a bit. Okay, I think that should be fine. Let me just do something like so log.info checking bucket d sure bucket index or just bucket. What is the problem here? Failed expected true found false. Okay, well that's not great. But what oh, okay, I see. Let's do debug.print. Let's not forget to add this annoying thing here. Okay, so let's see. We still don't have that code anywhere. Why is that? You can unlock 128 U8s. So wait, hold on. Can unlock 128 U8s. That should return true. All right, let's go here. Let's go here. Alignment N. Let's do debug print can unlock, and let's do size alignment in byte units and n. Sure. So size. So it's just called size alignment to byte units and then n. Okay. It's crazy that this needs to be added. Right, let's see. So failed can unlock 128. Expected true but found false. So does this go to can unlock? I think it does. So it should go here to our body allocator here. And it should probably go to somewhere around here. So let's do something like this. Can unlock this one here goes to requested length. The alignment is fine. And we don't have that, so we can just go ahead and do this. So can unlock 128 for 1. Oh, I see. So I think we are going to need to do the max order thing here. So, all right, let's do this actually. So can allocate. This one is fine. Check-in bucket 7. And let's do debug print found in bucket, something like this, and then here bucket. Okay, let's see. So check in bucket 7, found in bucket 7. All right, let's try again. Found in bucket 7, and here we can go ahead and can allocate. So 8, or rather a size that has a type that has a size of 8 with an alignment of 8 and a number of 3. So that gives us an allocation of 24 with an alignment of 8. We check in bucket 5, 6, and 7. And how did we not find this? How did we not find this? Because we could actually allocate that. It's fairly easy to do. We have memory of... Oh. Wait, hold on a minute. Oh, okay. I am actually kind of dumb. There we go. Right. So onwards to the next problem. Oh yes, of course, we haven't changed this one here. So 256. Cool, very nice. Okay. Phew. That should be okay. So we got the false here. Let me just do this just to check that we don't have any false positives. No, that should be fine. That was good. So can alloc, and I'm just going to get rid of all of these, that, and that should be all of them, and then go to allocator here. Probably get rid of this one too, and just rerun that. Cool. No more problems. Now, what were we doing actually? Yeah, we were here. Just about here. So allocator is now going to become our allocator, right? Allocator. Right, so now the config is a thing of the past. So let me just go, this is struct. Yeah, sure. There you go. What is your problem? Oh, found return. Cool. Nice. So now we bring back this. This takes a config, builds an allocator or fails, and this returns inner.allocator. Yeah. Yep, that's fairly okay. Now let's do the same thing here for heap, or fixed buffer allocator. Not sure what it takes. It returns allocator. Right. I'm guessing it should take alloc, which is instead mem allocator, which in this case, let's just call it adapt allocator. Sure. and this here would return. Okay, so we want this, and we want a can alloc, which is a function that takes in takes in a size, or no, an allocator, which is the mem allocator, takes in a size type uSize and an alignment of type alignment, stdmem alignment, and returns a boolean. Sure. So here we want pointer is alloc.pointer. Yeah, sure. vtable here, table is do that, and here we should do something like alloc is alloc. Ooh, this one is going to be vtable.alloc. Sure. Let me go ahead and copy those, because I'm lazy like that. Okay. Let's just put those there and do can alloc. This one is can alloc. This one is alloc.vtable.alloc. Whoops, we already have alloc.vtable.free, and whoops, alloc.vtable.resize, and then this one here is alloc.vtable.readmap. So are we ready for this? We should probably write a test for this somewhere here. So test adapt allocator, and then this what it should do is, so let's build a bit of a testing harness. So var buffer, let's go for 256, u8 is just go for this times 256, sure. And then we can go for var short fixed buffer is some sort of stdmem std heap fixed buffer allocator, takes in what nothing dot init. This one takes in a buffer, a slice to a buffer. Okay, so buffer should yeah, this, and then here we can go ahead and do const alloc is fixed buffer dot allocator. Right, and here we can go ahead and do const our alloc is adapt allocator alloc with test can alloc false. Yes, of course, this needs to be created. So function test can alloc false, which takes an allocator, which is stdmem allocator, and a size type uSize and an alignment of stdmem of type stdmem alignment, returns a bool, void, and returns false. Sure, it's okay. So we need now to do step testing dot expect equal false, and our alloc dot yeah, so we need to try that. Our alloc dot can alloc. How come this is not hold on a minute. What is this alloc? This is this type here. So yeah, it should have this can alloc function here. Cool. So this one takes in a type. So let's go for a U8 and a size. Yeah, sure. Let's go for 3. Oh yeah, of course. This is why it's wasn't completing. Cool. And then this we do. This is alloc. This is size and alignment. Okay, let's go ahead and do sig build test. Oh, I'm not sure if this actually is bold in tests. It's not. So import heap.sig. There we go. So, what are the problems? Allocator is not marked as public. What? Oh, okay. Public. Wait, what? Oh, because these ones are defined within themselves. Okay, fine. Expected type pointer function, but found usize mem alignment bool. I don't really see what the difference is. Oh, I see. It's the any opaque translation thing. So, thinking. Yeah, let's force this to just take in a pointer to any opaque. Sure. This we call self. I think the names are optional, but let's clear this up. Expect type. Okay, I think that takes in a pointer. Okay, so we need to change this also. So self is let's just call it pointer, I think. Any opaque, and this goes like so. Okay, segmentation fault, very nice. Can alloc advanced, can alloc with size, and for some reason the size of t caused a segmentation error. Hold on a minute. Okay, let's try to do something. So can alloc advanced and here thing. So let's go ahead and first check that we actually reach this with good arguments. So we can alloc the alignment, size alignment, and yeah, just size and alignment. So byte count and alignment. Sure. Oh, wait. What? The alignment was 0? Hold on. I'm going to need to replay that in slow motion. So the alignment was 0 for some reason. Okay. Okay. How come? What is this taking? This is taking a T and an N. Alignment goes to here. So let me just copy this, put this here. Here we have a few more things. We have at size of T, we have the alignment, and we have N. So size, alignment, and number. Of course. Oh, wait, hold on. Is that Y? 2 by 2 nets. Okay, so this one here can do something like, you know what, let me just go ahead and do any for that alignment there. So 1, 0, 3, and here we get, okay, so we do get the correct thing. Now. Let me also print, so debug print, and we can go ahead and print vtable just to make sure that it's correct. Let's do something like this and do self.vtable. I think we are just interested in can alloc. So this one is there, and that's exactly where we get the segmentation fault. Okay. How come we get a segmentation fault in here? There's no way this is the problem. No. Yeah, okay. So wait a minute. How come this is the problem? So can I just get rid of that pointer thing there? I can still get the issue at address, whatever that is. Yeah, okay. There's something that's not very good. What is the problem here? Let's just do something like this. Sure. Let's do this. what is this? Why does this function move? So I'm just thinking about why the pointer we get here should be this function's so let's try something else here. If we make it public, does it change where it's getting put? No. Keep that on, and right about here. So this, we should probably just put our pointer in there. And if we go now to our allocator, so here, instead of having this be vtable.any, we can do vtable.canAlloc. Let's clear this and rebuild it and see. Okay, so this function in the vtable is pointing to some other address for some reason. Instead, it should be pointed to this one here. So why isn't it doing that? Let's go back here to our adapt. We might be doing something very dumb. I cannot exclude that, knowing myself. Print, let's do that because it's annoying, and do any, sure. And here we can do canAlloc. Let me just do something here, adapt, yeah, just so we can figure out which is which. Looking for adapt. So this one is still okay. But as soon as we put it into this, wait, hold on a minute. There's something weird here. So yeah, this one is fine, but as soon as we put it into that vtable and we return that, we basically just get absolutely cooked. So I guess, do we just take this as a function, not a pointer to the function, and then we, I guess, just go again and see. Unable to format function body type use. Wait, hold on. Unable to format function body type use thing for function pointer type. Hold on. Not that. That should be okay. Okay, so why is it passing address 10 in there now? Does that mean that now I need to do this? Some weird shit going on. No, it's still address 10 for some reason. How come? Huh. Alright, I'm actually going to do something here. Let me try another approach to this. Well, first of all, this cannot raise an error. So let me just do this. Okay, this returns a type. this returns a struct that basically has this and has a function can alloc that has the correct parameters here. And returns a bool, and this one just calls. Let me just store that. So can alloc is can alloc, and of course we obviously need to put so any opaque here. This one here is a const function that takes in and any opaque AU size and a stdmem alignment and returns a boolean. And that's that. And this one here is a allocator.vtable. Sure. And that means that, yeah, so hold on. This one here, no, wait. This one becomes can alloc. This one here gets a public function allocator that basically takes nothing. No, it should take self. So thinking, should this be, hold on, let me just, yeah, it should modify the thing, so probably. So self at this and returns allocator. So I guess now we can just get rid of this, get that in here. Do something like this and put a return in here. And of course that. And pointer gets self.pointer. This is a different approach here. So let's go ahead and do return false just for a bit. And obviously we need to just go ahead and do this here. Let's see, we should probably have a few, let's go, compilation problems here. Unable to resolve comp time value alloc. Comp time. Wait, is that really comp time? It's not a comp time value. What are you talking about? Right. So what is the problem with this thing? So unable to resolve comp time value in our allocator. Call to function with comp time only return type is evaluated at comp time. Well, how about this? So this is a pointer to const function. Oh, because this is returning a type, so now it wants this to become a comp time known. Right. Okay, so well, that just means that now I don't need to create this. Right, let me do this again from scratch. So const allocator adapter is a struct that basically has a function, public function in it, takes in an allocator of type std allocator, and takes in a can alloc function here. Should probably just go ahead and copy that. Sure. Returns this, right? And this is basically this, but within, so return something like that. So here we need to basically do that again here. This time, just like this. And here we can just drop every up to that point. And of course, we need to go here and do something like this. All right, that works. Now we need to get this. No, actually, we need to get both of these, put them into here, and get rid of this thing here. Right. So we also need to store. So think in. We need to store alloc. No, because we just need to do this actually. Yeah, we just need to store the allocator actually. So std allocator. So with this, I think we should probably be okay. So let me just do this. This becomes alloc. This actually becomes self dot alloc dot pointer. This becomes self dot alloc. So all of these become self dot alloc dot something. And this should do the trick. So let me go ahead here. This one goes, and we can go ahead and create. So this one here becomes allocator adapter, right? And this one becomes init with these two things here. Right, let's see. No field or member function called alloc. Can alloc in heap allocator provider. Okay. Let's call this adapter. Let's go ahead and do const our alloc is adapter.allocator. That should do it. Okay, so now we are back to where we were before. Same damn problem. Same segmentation fault. This time we are not using any of the things here. So we just call in this can alloc function here. So it should should just hit this and go. Called Kernel lock. And of course we need to do this. Right, so what am I missing here? Just going to check something, because in our body allocator here we actually have like some very usable things, and this does work. So I'm just going to check if it's not the pointer that's basically bad. No, here we get an allocator, so it should still be fine. The pointer is basically this allocator here. So no, debug print. So alloc dot pointer. Sure. So init with any opaque. Hold on, is this allocator pointer here bad? No way. Hold on, let me just try this again. So we are calling init with any opaque and this address, and that's the address we have our vtable at. So I think there might be a problem. How come? Should this be taken a pointer to an allocator or something, just to avoid copying the actual allocator? Let's see. Oh, of course. This needs to drop the const. No. Const should be fine. This needs to become const. Pointer to const. Explicit type memory allocator, but found pointer to const memory allocator. That's actually fine. So let's get some more pointers going, and we still get the same problem. This time there's a slight improvement here, because the address at which we segfault is different from the address that we put into the thing, but that just means that I don't even know what that means, to be honest. So let's go back, way back. Let's go to how this was in here. Right, so let's do something a bit more meaningful here. Just going to dump the allocator that is given to us by fixed buffer allocator and our allocator here. And see what the differences might be. Here pointer is the same. vtable. This one is kind of lock, but if we move here, we have alloc, which is 1224. This one is 162. That's weird. Resize is 1162, and this one is 1162 ed0. That's correct. 1163 to f0, and then 1163 to f0. And free is at 1163 3b0, 1163 3b0. So all of them match except alloc. and obviously can alloc. Right, so that puts us on a somewhat of a gives us somewhat of a clue. So let's just create our own allocator here. Let's do this. Pointer would be just alloc.pointer. vtable would be something like this with yeah, cannot be bothered to do this. So let me just do self dot goes, and this one here becomes just test can alloc false. This is not used. It's fine. Right. So let's try to see. Okay, so it's not crashing. Does that mean that we have all of these be the same? So this one is alloc. Okay, so this one is can alloc. Let's move. So this one is 1162b80, 1162b80. 1162ed0, 1162ed0, 1163 to f0, 1163 to f0, and then 633b0, 1163 3b0. So when all of the pointers align, we only get the problem. But when we created the allocator with this, for some reason it was not correct. And what was not correct is actually the alloc thing. So yeah, kind of weird. It's the exact same thing that we did both here and here. And actually, maybe we can just drop that. So adapt allocator. Let's try this again with a fresh mindset. So this takes in an alloc of type submem allocator. Sure. Let's for now say that it doesn't take a function pointer. Let's just go ahead and assume that the function exists elsewhere. And let me just copy this exact code here, except that instead of doing this, I'm just going to hit return. We're still pointing to the exact same function here. So this returns false for us. Okay, so now let's go again and try to do this adapt allocator, except that this time it doesn't take that. So let's also print this guy, adapter. What's your problem? Const. Sure. Right, let's zoom into this and print it again. So this time, again, it does work. Except that the can alloc pointer is wrong. Wait, what? No, all of them are wrong, actually. Huh, I see. Yeah, so all of them are not good. Okay, I think I see what the problem is. The vtable is passed as a pointer, and that makes it so that when we move this back, these pointers here just basically can get wonky. So how could we fix that? Let's try. Let's try this. Other alloc should be a some other stdmem allocator here, and we can do var vtable is a pointer const pointer to vtable to stud to allocator.vtable, right? And this one would be other alloc.create. Well, allocator.vtable. Well, that means that we did not have to do this. So now this needs to be tried. This needs to be to return a thing, and then here we can do vtable dot star is equal to these things. So I guess this one can remain constant, and here we can do vtable is vtable. Sure. Let's see if this works now. Actually, we need to so const testing allocator alloc is testing dot allocator. Sure, and we use that here. Testing alloc. All right. Let's see. So I guess we have a leak issue, but that's the least of our problems for now. Yeah, so here, again, we can see that we do have the correct pointers now. Hold on a second. Yeah, they are correct. So that was the problem. So can we avoid that now? One thing we can opt for is to make our vtable here, instead of being a const pointer, just have it live on the object itself, which might make the allocator itself a lot larger, or we could just live with that. I guess we could just live with what we have. So let's call this alloc, and let's call this allocator or adaptee. Sure. So this here, everything goes from alloc to adaptee. Sure, this one here goes back to alloc. Okay, and then this one is adaptee dot pointer. So now we can get rid of all of this, and now we can go ahead and take a canalloc function here as a const function that takes in a pointer to any opaque, a usize, an alignment stdmem alignment, and returns a boolean. And here we can just go ahead and do can alloc and hope for the best. Right, so let me try to do, so let's keep that. except that here we are going to do adaptee, or rather adapter. Okay, so expect 3 arguments found 2. That's actually fine. We can do something like this now. Should still be okay. Try. Wait, no, this is the only thing that needs to be tried. Okay, so still same error here. What are we missing? No, this is a leak, which is good news. So let's fix the leak. So this one here, this allocator is, so we just need to free its fee table, basically. So we can defer this thing alloc dot destroy adapter dot fee table. And that should do the trick. Yes, it does. So let's can alloc. Let's try to find where we've put those. This can go. This can go. Okay, so now the only things that remain are in heap, and those should be these things here. And this one. And obviously now we don't need this, our allocator. Right, so now, now that we are here, we still need to do something because let's think for a second here. We would like to adapt an allocator, but we would like also to avoid creating a bunch of fee tables. Or rather, we want to avoid having to do this, basically. So we might want to, I mean, we could choose to not do anything about it, since all adapters that we all adapters that we create for any allocators will have a basically static lifetime. So they would only go out of scope when our operating system or when the kernel stops, and at that point we don't really care about freeing memory. So that's a valid thing we could do. Otherwise, we can just queue them somewhere, put them into a list, and when we exit our kernel, we could probably think about destroying them. But you know what? That's a problem for the future. I'm just going to take this, put that there. Just going to check that we still run the tests correctly. Fine. So, I think that's as far as I'd like to go for today. I'm pretty sure this was fairly long. Yeah, it was fairly long. But we are on the right track, I think, to make something very nice to use. That's it for this one. It's been a bit more chaotic than usual. As always, if you've liked this video, hit like, subscribe, and if you have comments, remarks, or you just want to say hi, just leave them in the comments down below. And I'll see you next time. Fucking hell.